Understanding this picture makes pointers far less mysterious when we get to them, so it is worth 5 minutes now. A running program divides its memory into regions. At the bottom, at low addresses, sits text, your machine code, and usually your string literals. Above it, data, holding initialized globals and statics. Above that, BSS, holding the uninitialized ones. Then the heap, which grows upward as you allocate. Then a large gap. Then the stack, at the top, growing downward as you call functions. And right at the very top, your command line arguments and environment variables. The gap in the middle is what the two growing regions eat into from opposite ends. If they ever meet, you have run out of memory in the most dramatic way available, and if it is the stack that arrives first, which it usually is, that is a stack overflow. Let us take the regions in turn. The bottom 3 regions are decided before your program ever runs. Text holds your machine code, it is mapped read-only. And the operating system will often share 1 copy between every process running the same program. Run 4 copies of your editor and there is still only 1 copy of the code in physical memory. String literals usually live in text too, and that is the answer to a question that puzzles every beginner. Why does modifying a string literal crash? Because it is sitting in read-only memory. Data holds globals and statics that have a non-zero initializer, and those values are physically stored inside your executable file. BSS holds the ones that start at 0. Here is the neat part: BSS costs nothing in the file. It is recorded as a size, and the load is zeros that many bytes at startup, which is why a global array of 1,000,000 zeroed integers does not add 4 megabytes to your binary. The stack is where your locals live, and it is beautifully simple. Every function call pushes a stack frame containing the parameters, the local variables, and the return address. Returning pops the frame off. That is the entire mechanism. It costs approximately nothing, adjusting 1 register, and it is precisely what automatic storage duration means in hardware. It is also why the address of a local is only valid while the function is running, which we saw go wrong 3 lessons ago. But it is finite, and smaller than people expect, 1 to 8 megabytes on a typical desktop, and far less on an embedded target. 2 things exhaust it. Recursion that goes too deep, because each level costs a frame. And a single enormous local array. Declare 1,000,000 integers as a local and you have asked for 4 megabytes in one go. Declare the same array as a global and it lives in BSS instead, and everything is fine. And the heap, which is the opposite of the stack in every respect. It is manual and it is flexible. You choose how much memory, and you choose how long it lives. You can decide the size at runtime from a number you read out of a file, which the stack cannot portably do. And crucially, it survives the function that allocated it, so this is the honest answer to the dangling pointer problem from earlier. If the caller needs to keep it, put it on the heap. The price is that nothing cleans it up for you. Every malloc needs a matching free at exactly the right moment, not before anybody has finished with it, and not never. Forget it and you leak. Do it twice and you corrupt the allocator. Do it too early and you are back to a dangling pointer. Chapter 12 is devoted to getting this right, and it is the chapter where C stops being a nicer assembler and starts asking you to be careful.